Hello, welcome back. We are going to continue our discussion on how to connect LEDs in various ways, LEDs and RGB LEDs and even 7 segment displays. So, let us begin. Now, here if you look at this diagram that I have drawn, here my microcontroller is MSP430 for example, and I have shown that I have connected 4 LEDs in 4 different ways. This is to ensure that you understand that LEDs are can be seen as binary devices, binary output devices, which means either the LED is on or off. There is another way to control LEDs where I would like to change the intensity of an LED, which we will consider in a latter part. But here let us see how we can. So, if you see this is wrong, this is output OP1. In the output 1 I have connected the LED with the resistor R1. At the output pin number 2 I have connected the resistor first and another LED. On output 3 I have now used a different configuration. I connected the LED first and then the resistor R3, and for output 4 I have connected the resistor 4 first to the pin of the microcontroller and then the LED. Now the question is, how different are they? All same or are they very different? Well, the answer is that LED 1 and LED 2 are identical. These are LED 1 and LED 1 and 2 are identical in connection, and LED 3 and 4 are identical too, and they are different from LED 1 and 2. How? LED 1 and 2 would light up when the output OP1 or OP2 is high, that is logic 1. On the other hand, LED 3 and 4 would light up when the output of these pins, that is OP3 and 4, is logic 0. And so, these two LEDs will be called as active high, meaning they are lighting up when the output is logic 1, and these two LEDs will be called active low outputs, they are lighting when the output is 0. Also, we are controlling the high side of the voltage for LED 1 and 2, that is why we have written high side control, and for LED 3 we are controlling the lower potential of these LEDs, so we call it low side control. And now let us see what should be the value of resistor R1 and R2, because R1 and R2 will be same value because the two configurations are same, whereas R3 and R4 are also same, but they might be different from R1 and R2. How should you select the value of these resistors? That is an important point. So, first of all, for that we have to consider what is the voltage drop across the LED. Now, most of the time when I ask this question to beginner students, they say the voltage drop across LED is 0.7 volts. For some reason they think that the LED is also a normal silicon diode, but that is not the case. In fact, the voltage drop across LED, voltage drop across, and here I mean in the forward region across LED, depends on color of the LED. And we have the entire range of LEDs available, which emit different colors, and they might be VIB, GUR. You might have red colored LED, you may have orange, yellow, green, blue, indigo and violet. So, it turns out that if you have a red LED which has the smallest energy, this has the smallest voltage drop across it, whereas the violet or blue in this range, as you go to this these colors, the voltage drop across the LED increases because the band gap required to emit these colors is more, and therefore the voltage drop is more. Typically a red LED has a red LED requires about 1.6 volts, and as you go towards blue, the voltage goes from 1.6 to maybe 2.2 for orange and yellow, maybe for green about 2.5 volts, and for blue roughly 3 volts. And so you must consider this when you are designing a system to control these LEDs. Let us go back. Now here we see we have the VCC here. Now if the VCC itself is 3 volts, then it may be difficult to control a blue LED, but MSP430 can, the supply voltage can go up to 3.6 volts. So we can power this with say 3.6 volts, and we would be able to connect blue LEDs also. However, in the calculations we must use the voltage drop across a forward voltage drop across an LED appropriately, so that we can estimate the value of the resistors. So what all we need to know? We need to know what is the voltage drop across the LED. Secondly, to control these LEDs we need how much what should be the value of the resistors, and now the question is how to calculate. Now the two calculations for the two setups are different, and let us go through those calculations. In the case of a high side control, meaning I have the LEDs set up so that they will light up when the output voltage is high here in this case. So let us say this is R1, and let us say this is some LED, let us say this is our red LED. And I do not have to use exact values, I will use symbolic values here. So when I turn the logic of the pin to logic 1, when I turn the pin to logic 1, the voltage of this will be VOH. The voltage across the LED will be VLED. You can find out from the data sheet that what is the voltage drop across a red LED. This difference is the voltage across R1, and therefore the current through this will be I is equal to VOH minus VLED divided by R1. Now suppose you want 5 milliamperes of current. Let us take some numbers. Let us say VOH is 3 volt, if your VCC is say 3.6 volts, this is equal to VCC, and let us say VOH is equal to 3 volt. The exact value you should find out from the data sheet. Let us also assume that VLED for a red LED is say 1.6 volts, and let us say we want the current to be equal to 5 milliampere, and therefore this becomes 3 minus 1.6 upon 5 into 10 to the power minus 3 amperes. This is 1.4 divided by 5 kilo ohm. So this is 1400 divided by 5 ohm, and this is roughly R1 will be equal to roughly 300 ohm, and you can safely use a standard value of 270 ohms in this case to allow about 5 milliamperes of current through the LED. On the other hand, if you want to control the LED in the low side control method, then your configuration will change, and it will be, here is my microcontroller MSP430. My VCC is set to 3.6 volts, here is my ground, and here is my output pin, say output 1, and I have connected the LED in the low side control. Here is my VCC, and this is now say R2, and this is still red LED. As I mentioned earlier, the LED will be turned on when the output 1 is set to logic 0, but when the output is set to logic 0, the output voltage is not 0 volts. In fact, the maximum value of voltage that you will get will be VOL, and we can go to the data sheet to find out the value, but let us assume that VOL is say 0.4 volts. We will still assume that VLED for this red LED is equal to 1.6 volts. My VCC is here 3.6 volts, the VLED is 1.6 volts, the VCC is 3.6 volts, and we want to estimate the value of R2 from the current that we desire through the LED. Let us say the current we want through the LED is also 5 milliampere. Now, the calculation will be 3.6 volts minus VLED, which is 1.6 volt, minus the VOL output, which in this case is 0.4 volts, divided by 5 milliampere. Therefore, the resistor R2 is equal to 1.6 volt, because this is 2 minus 0.4, 1.6 divided by 5 milliampere, and now this is about 1600 ohm divided by 5. So, this would be roughly 320 ohm, and so you can R2 is 320 ohms, and you can use a standard value of 330 ohms for allowing about 5 milliamperes of current through this configuration. Now, what if you wanted to increase the current through the LED through either of these configuration, whether low side or high side? Let us see that. But before that, let us see, other than the LEDs, individual LEDs, what all can we control, and in this case here is an example of a 7 segment display. A 7 segment display is actually a misnomer, because there are 8 segments as you see here. You have A, B, C, D, E, F, G and a decimal point. So, really there are 8 LEDs in a 7 segment display. Now, these 7 segment displays come in 2 varieties. One is called common anode, which means this display internally will have 8 LEDs, and their LED, the anodes will be connected together. So, you would have 8 LEDs, this is the, so this terminal will be called common anode, and you would have A, B, so on and so forth up to DP, and the other, so this is common anode. The other type of LEDs, 7 segment displays, are called common cathode, where what do you have is that the cathodes of the LEDs are all connected together like this, and this terminal will be called CC, that is common cathode, and here are the actual inputs. So, this is your A, this is your B and so on, and this is your DP, that is decimal point. Now, how can we connect these 7 segment displays to microcontrollers? Let us look at this scheme. So, I have shown here that a microcontroller, in this case let us say we are talking of MSP 430, that we have 2 ports, this is port 1 and this is port 2, each port has 8 outputs, and we have used common cathode LED here, and we have used 8 resistors. And how to calculate the value of the resistors here? Because here common cathode, the common point is grounded, that means what sort of control will you be exercising? This will be high side control, that is when an individual port pin here is set to 1, it will turn that LED on. If you want to turn a LED off, a segment off, that port pin will have to be set to 0. The value of the resistor will be calculated in the same way as this calculation. Why? Because the cathodes are of each of these LEDs are grounded. So, I do not have to repeat that discussion here. Another method to control connect these LEDs, instead of common cathode LEDs, you can have well, here is another variation to that. Now, you may wonder that instead of connecting using 8 resistors, can you connect use a single resistor like this, and this way you can save 7 resistors? Well, this may seem like a good deal, but this will give you unequal intensity of the LEDs. Now, imagine that you want to turn only one LED out of these, maybe you want to just display a bar. So, this particular LED you want to turn on. So, the corresponding pin will be set to 1, the rest of the pins, output pins will be 0, which means this resistor, the current that can flow through this configuration is going to, all that current is going to flow through one LED. So, it will grow bright. Now, imagine that you want to display 1, which means you want to turn this and this LED on. Now, this same current will be shared by 2 LEDs. So, the LED intensity will become half. Similarly, if you, so you display dash, you will get certain intensity. When you display 1, you will find that the intensity has become half. If you display 2, which will look like this, how many LEDs have you turned on? 1, 2, 3, 4, 5 LEDs. That means the current through each LED becomes 0.2 times the maximum current. So, each LED will be roughly lighting up with 1/5 the intensity. And so, although this appears to be economical method because it uses only one resistor, what you will end up having is that as you change the display numbers, the intensity of that display would vary, and therefore, it is not very recommended to use this configuration. And so, one should use all kinds of one should use a resistor on all the pins as mentioned here. Also important to know is you have to know which segment is connected to which pin of the port, because in the software this will be used so that you can display numbers or any other symbols on these display, and we will cover that when we do an exercise to control 7 segment displays using MSP430. Right now we are only looking at the electrical aspects, the circuit aspects of controlling 7 segment displays. The second method would be to use common anode LEDs. Now, here the anodes are common, therefore, it is connected to VCC, and the cathodes are the segments which is A, B up to DP, they are connected to port pins. This is your MSP 430 microcontroller, and here the calculations will be same as we saw. This is low side control, and so the calculations would be what we did is equal to, the resistor value will be equal to VCC minus VLED minus VOL divided by the current that you require. This is the value of the resistor, and you would have all these 8 resistors equal to this value, as we estimated in the last calculations for 5 milliamperes of current and red display, 7 segment display. The value of resistor, each one of these will be, I think we got a value of, let me go back and check, this was 330 ohms. So, in this case you can connect all these 330 ohm resistors, 8 of them like this. And here I have shown that we have connected 2 digits. So, we can use this to display numbers from 00 to 99, or if you want to display hexadecimal numbers, you will be able to display from 00 all the way to FF, which means you can display a total of 256 values on this these 2 sets of displays. Let us see what else we can do. Now, imagine that we want to increase the current through each of these LEDs, that is, you want to turn these, you want to drive these LEDs more brightly, then you would require a transistor here as I have shown, and we are going to take this discussion forward in the next few slides. Now, here is what I meant when I mentioned that what if you wanted to increase the intensity of the LED. Now, each of the port pins of the microcontroller has only a limited amount of capability. As we have seen for MSP430, the maximum current that each of the pins can provide you is about 6 milliampere. And so, what if you wanted to drive the LED with say 20 milliamperes of current? There are 2 ways. This is the first method. If you have multiple pins available, spare pins, then you can connect 4 resistors to drive a single LED, and If you want 20 milliamperes, you can share it each of these to be 5 milliamperes, and so together you can drive 20 milliamperes through LED 1. Of course, it requires 4 resistors, and the value of the resistor will be calculated assuming that you want 5 milliamperes, and so I think this is, if we go back here, we can see the calculation here. Well, no, this, the configuration is this one, and so here we have 330 ohm. So, if you want the low side control of the LEDs and more current through the LED of say 20 milliamperes, you allow 5 milliamperes each, and the resistors, all resistors will be 330 ohm. Now, with this you can turn the LED on by making all these bits set to 0, and you want to turn the LED off, then all these bits will be set to 1. Now, this configuration also has an interesting side effect, that instead of all the output pins turned to logic 1 or logic 0 will turn the LED completely on or completely off. What if you turned only D0 equal to 0 and D1 and D2 and D3 are set to logic 1? You will see that the intensity of LED will go from minimum to maximum, and you can actually control the intensity also, not just in a binary way 0 and 1 LED on or LED off. You can have a various levels of intensity in the LED. The other method of increasing the current through the LED is shown in the right side of this diagram. Here we have used a NPN transistor here to control the current through the LED. Why? Because since the microcontroller pin cannot provide say 20 milliamperes of current, we will choose an external transistor and we have to select the transistor appropriately. So, let us continue with this firm example. Our requirement is that the LED current I LED is to be 20 milliamperes. Our microcontroller cannot provide 20 milliamperes of current, so we have to connect an external circuit which we saw in the previous slide. Let me redraw it here for easy reference. Here is our microcontroller, here is the output pin, let us call it OP1. It is connected to a resistor which we label as R1. Here is the NPN transistor. We have to choose a low side switch, and so we choose the NPN transistor as we discussed earlier. The supply voltage is 3.6 volts. Here is our red LED. The choice of LED is important because knowing what LED we are going to drive will allow us to know what is the voltage drop across the LED. And here is our current limiting resistor through the LED, we call it R2, and this transistor is T1. Now we can choose any transistor, NPN transistor, that will offer a maximum collector current which is much more than the load current. The load current in this case is the current through the LED, which we have decided to be 20 milliamperes. So, as long as the transistor is able to handle much more than 20 milliamperes, any transistor should be fine. Now, how much is much more? Let us say if we use a commonly available transistor which we use in our undergraduate electronics laboratories, BC547, then we know from the data sheet, of course, that the maximum collector current IC max for a BC547 is 100 milliamperes, and so such a transistor would be quite suitable. You could of course choose another transistor which has collector current more than this. Apart from the maximum collector current that that the transistor offers, we also have to look at the data sheet of the transistor to find out what is the saturation voltage, collector emitter saturation voltage, VCE sat, because that is going to come in this loop in the calculations for calculating the value of R2 and subsequently for the calculation of value of R1. For BC547, the saturation voltage is typically in the range of 0.1 volts to 0.2 volts. So now we have to calculate the value of R2. So R2 into the collector current, that is I LED, that is this volts, plus VLED, the voltage drop across the LED, plus VCE SAT, as we see here. Here is the VCE SAT, VCE saturation. All the sum of these three elements will be equal to the supply voltage, which is 3.6 volts. Now, what is the voltage drop across a LED? That of course depends on the color of the LED. And if we choose a red LED, typically the voltage is 1.6 volts. So we are going to use that as a reference. Of course, for a particular LED that you use, you must find out the value of the forward voltage drop across the LED for the given current. What is that voltage? You must plug it into this equation. So let us solve this equation for the value of R2. So R2 is equal to 3.6 volts minus 1.6 volts for the voltage drop across the LED minus VC SAT, and let us choose this 0.2 volts as the saturation voltage for BC547 divided by 20 milliamperes, because that is our load current. And so this becomes 1.8 volts divided by 20 milliampere, and this returns the value of R2 to be equal to 90 ohms. Of course, 90 ohms may not be a standard resistor value, so you must choose the nearest resistor value to 90, and I can tell you that the nearest value is 91 ohms, which is very close to what we actually need. And so R2, the value of resistor R2, turns out to be 91 ohms. Now, having a value of resistor is important, but also selecting an appropriate resistor which can dissipate the power is also important. In this case, we must find out what is the power dissipated by R2, so that we can choose a resistor which can dissipate more power than that, so that it operates in a safe region. Now here we can use the PR2, that is the power dissipated by R2. We can calculate using I square into R, which in this case is 20 into 10 raised to the power minus 3 milli, that is amperes, into 20 into 10 raised to the power minus 3 into, for sake of ease of calculation, let us plug the value of R2 to be 100 ohms. And so this gives me a value of 40 milliwatt. If you go through this calculation, this is what you would get, 40 milliwatts of power. And a typical 5% quarter watt resistor means 250 milliwatts. That would be quite suitable to be used in this configuration. So we have seen that what equation to use to be able to calculate the value of the current limiting resistor with the LED. Now, if you want to change the value of the current from 20 milliamperes to say 100 milliamperes, you would still use the same approach, but find out a suitable transistor to replace BC547, which will be able to give you what you need. Which will be able to handle 100 milliamperes. So if you want to conduct 100 milliamperes through the LED, you must choose a transistor which is say 200 or 500 milliamperes of maximum collector current. And you can go through these equations again, plug the values appropriately and estimate the value of R2. Now that we have the value of R2, we must also estimate the value of the base resistor. What is the value of the base resistor here labeled as R1? Let me take you through that equation, and for ease of reference, let me redraw the circuit here. We have value of R1, our transistor T1, which in our case we have decided it to be BC547. We have the supply voltage of 3.6 volts. Here is our red LED, which is going to be driven with 20 milliamperes, and our value of R2, which we have estimated to be 91 ohm. Now we are left to calculate the value of R1. Here is our microcontroller. Now a microcontroller will turn the LED on when the output is logic 1. So OP1, when OP1 is 1, it will turn the LED on. Now, when the output of a microcontroller is set to 1, it means it necessarily is logic 1, but it doesn't mean that it will have the same voltage as 3.6 volt if it is also driven with a supply voltage of 3.6 volts. It's not necessary. So what we have to find out from the data sheet of the microcontroller, that what is VOH, that is the output voltage when the output is high. What is the VOH for that given microcontroller? And in this case, from the data sheet, let's assume that it is 3 volts, 3.0 volts for VCC equal to 3.6 volts. Now we have to, our collector current is 20 milliamperes. We must saturate the transistor. The nominal base current that will be required to maintain 20 milliamperes of current, the value will be IB is equal to IC by beta, that is the current gain of this transistor. BC547 is available in many varieties, and the simplest value that the simplest version of this transistor has a beta of about 100, and so our base current that we require will be 20 milliampere divided by 100, which turns out to be 0.2 milliampere. Now, to ensure that the transistor is driven strongly into the saturation region, we must provide base current which is much more than this value. Now, how much more is much more? Well, a value of 2 or 3 times or even 5 times more than this current would be suitable. So let us first estimate the value of the resistor R1 for current of 0.2 milliamperes, and then we will reduce it by a factor, say factor of 2 or 5, so that we are sure that transistor T1 is driven deep into the saturation. So for this, VOH, that is the output high voltage, is equal to the voltage drop across R1, which is IB into R1 plus VBE saturation, because we are driving the transistor in saturation. For typically the turn on voltage for a NPN transistor, the base emitter voltage is 0.6 or 0.7 volts, but when you drive the transistor in saturation, this voltage is slightly higher. And let us you can refer to the data sheet, and it will tell you that the saturation base emitter saturation voltage is say 0.9 volts. So we have to find out the value of R1. Therefore, R1 is equal to VOH, which we have estimated to be 3 volts. 3 minus 0.9 volts divided by base current, which in this case is 0.2 milliampere. So the value of resistor, this calculation shows 2.1 volt divided by 0.2 milliampere, and therefore the value of resistor turns out to be approximately 10 kilo ohm. Now this is the minimum current that you would require for the base current, but to ensure that the transistor is driven strongly into saturation, we must provide a base current which is 2 or 3 times or even 5 times more than this base current, and so it will reduce the value of this resistor by that much factor. So let us say that we want 5 times more base current, so it will reduce the value of R1 by a factor of 5, and so R1 should actually be 10 kilo ohms divided by 5, 2 kilo ohm. So now we have the values of all the components that are required. R1 is 2 kilo ohm. R2 we have already estimated to be 91 ohms. Our transistor is BC547, and we have chosen a red LED, and in this configuration the microcontroller will be able to drive 20 milliamperes of current through the LED. And this is the process, these are the steps that you must take to be able to design all the components to arrive at the values of the components for a low side switch as we have illustrated. We will resume this discussion in the next lecture. Thank you.